So I'm going to be talking about hunting for the biggest black holes in the universe. And the work I do is sits at this kind of interface between stellar observation, galaxy formation, gravitational waves, and black holes. So I'm going to do my best to convey kind of the range of this field and highlight my work within it. Because I can't sit still. I've worked on a bunch of different aspects of this field. I'll try to highlight a lot of these. This is in two parts. Part one, pulsar timing arrays. So my good friend Chiara Mingarelli works here, and she reassured me that not everybody might know the depth of pulsar timing arrays, so suggested I introduce them. And as Max is saying, there are these very, very small black holes that orbit. They're pretty big. They're 100 solar masses or so. And LIGO is able to detect these, and it has been, and this is in this wonderful break into this field of gravitational science and multi-messenger science, where they're able to track the electromagnetic emission from these objects. But you can move down in, up in, down in frequency, up in timescale of orbit, and get over to LISA band. And these objects are orbiting much more slowly. And because we know about Kepler's laws, we know that they're a lot further apart. So to make very bright gravitational waves, they just have to be a lot more massive. So here I have this animated panel showing the signal that we're going to take, which is orbiting on terms of like weeks to decades. So pulsar timing arrays detect the absolutely most massive signals in the universe, coming from the most massive systems in the universe. And this is above 10 to the 8th solar mass black holes. And I've got this funny little question mark here. The talk I'm going to give today is talking about work that was published a couple of years ago, but it was the latest result that came out of nanograv collaboration. And I'm going to give you at least an outline of the sort of general plan going into the future. And here's kind of a slide on the human aspect of this. Pulsar timing arrays are people who are using radio telescopes to observe pulsars in the sky. There are pulsar timing array contributors all the world around. Unfortunately, Arecibo is now collapsed. This was one of the biggest contributors to the North American Nanohertz Observatory for Gravitational Waves, which I'll call NanoGrav for the rest of my talk, which involved Arecibo, Very Large Array, and Green Bank Telescope in a North American-led effort to detect gravitational waves. That's been going on for just over 15 years, nearly 20 years now. Similarly, in Europe, using European telescopes, there's the European Pulsar Timing Array. Parkes Pulsar Timing Array has been led by the Parkes telescope. And the Indian Pulsar Timing Array has been led by scientists in India, largely working at GMRT. I list these out specifically because these four groups have, over the past couple of years, been forming this International Pulsar Timing Array, which is aiming specifically to do this kind of cross-validation of our data and our procedures. So we work loosely together, although we work independently on parallel problems. So the idea is that we're coordinating to try to come up with an answer about the same science. And if one of us is doing it wrong, we tell them. That's the main idea. But I will say that Meerkat has this. Well, Meerkat is the telescope down there. That is now doing pulsar timing, and the FAST telescope in China has been going for a couple of years now, and seems to be coming up with some data that will contribute to all of these efforts. Now, pulsar timing generally is, of course, we're using these radio telescopes to observe a pulsar. Here I'm showing this beautiful pulsar profile from my favorite pulsar, JO47, minus 3714. I think that's its digits. I feel like I said that wrong. And of course, we know what pulsars are. They're these rotating neutron stars. But what's interesting about pulsar timing is that what we're doing is just continually, just about every 2 weeks, taking an observation of a pulsar. And we average it over a course of something like an hour and get a profile that looks like this. These profiles are very stable. This is representing one rotation of a pulsar. So you see when it beams across you, you get this really bright spike. Over time, if you don't have a good model of the pulsar, you might look back at the same spot in the sky and predict when the next pulse will arrive. And if you've done it wrong, you will have a slightly offset pulse. And if that is the case, it means that you really haven't modeled correctly in your prediction for that pulse arrival time for one of these properties, right? some kind of unmodeled physical effect. So the pulsar is spinning, maybe you got the period wrong. It's spinning down because it's releasing energy all the time, so that spin is slowing. Maybe it's in a binary. Maybe there's some interstellar medium between you and that. Of course there is. So we have to model for all of those things. But if we perfectly account for those, we get some pulsar data that looks essentially like this. And this is the actual pulsar data set. This is a pulsar I observed with Parkes years ago. And it's plotting the model arrival time based on fitting for all of these properties minus the actual arrival time. And you can see that, arrival phase is in microseconds. We call these timing residuals because it's just the residual signal. And you can see it's pretty bang on zero with a spread of maybe about, 200 nanoseconds. So that's pretty good, well timed. Now, pulsar timing arrays are really amazing because you can get really precise measurements of pulsars. And pulsars are wonderfully regular spinners. And it essentially makes them like just a ticking test mass in space, right? So the idea of a pulsar timing array is not the array of telescopes, it's the array of pulsars. And at this point around the world, we're observing something like just over 100 pulsars around the galaxy. So these are all galactic pulsars. We're observing each one. We make a model for each one and get really fantastically precise spin precision for each pulsar and make residuals. Okay, so if we fit for all the things we know about, look, there's a sinusoid because Earth's moving around the sun. There's some wandering term because our clocks on Earth are not totally precise, but we can correct for that. We correct for all those things. What's left is anything affecting Earth that we haven't modeled. And one of the things that we haven't necessarily modeled is gravitational waves. So over off in a distant galaxy, you might have a binary black hole, and it's gradually orbiting, sending off this continuous stream of gravitational radiation, which is coming across our galaxy, hitting the pulsar and Earth at slightly different times because they're at different locations of the galaxy, and oscillating the space-time at Earth, which changes how we see this pulsar, right? It looks like Doppler shifted away and towards us. So it changes that spin, perceived spin frequency a little bit. We also see the gravitational wave affecting the pulsar itself. So the net effect we actually see is the addition or difference between those two terms, the pulsar term and the Earth term. Do this for many pulsars and come up with some data. So this is a simulated gravitational wave data stream where I've stuck in a really bright gravitational wave source, probably like, a couple megaparsecs from our galaxy. That's some like 10 to the 9 solar mass binary, which is completely unreasonable. But it makes this really fantastic signal where you can see one orbit basically traces out two cycles of a sinusoid in this space. And you can see here kind of very literally why we are sensitive to the frequency range we are. So we can detect signals on timescales of weeks because that's essentially the Nyquist sampling. We take samples every 2 weeks. And we can detect signals that are up to a couple of decades in frequency because the slowest binaries will trace out a sinusoid on the timescale of our data set. And you can see that the sinusoid is actually changing a little bit over the course of the data. And that is due to that pulsar term difference between the Earth term. So you end up with this not perfect sinusoid. That comes into play later when I talk about other things. So we think that binary black holes exist in the universe. I'm going to talk about them in more depth a little bit later. But what I wanted to point out is that when we deal with pulsar timing, there are a couple of different ways we expect to see these signals in our data. The one I just showed is what we call continuous waves because it's just this continuous stream of waves on an ocean, right, in outer space. If you have a universe full of binary black holes, there's millions to billions of these contributing to the signal. And you have to add up all of those noise, what effectively is a noise source, and note that you will end up with this sum of sinusoids. That is a simulated gravitational wave background that I'm showing in the upper right, what the residuals would look like. And you can see again, I'm plotting 3 different pulsars in different colors and symbols. And you can see that it's sort of just a red noise process, right? It's kind of like just a red noise random walk. More signal at low frequencies than high frequencies for each of those pulsars. Doesn't necessarily look exactly correlated, but definitely has similar noise properties. I'm not really going to talk about coalescence, but we can, in principle, detect the moment of actual coalescence of a black hole by the fact that it just permanently deforms space-time, and suddenly all of our pulsar periods would be wrong. So that's possible, but it doesn't happen very often for 10 to the 9 solar mass black holes. It's like kind of a once in a century kind of thing. You know, give us another 80 years and we'll detect one. So I wanted to just say briefly, I don't like putting equation slides out, but some people like equations. I've been walking around these hallways. I added this like 20 minutes ago. I was like, they'll like the equations. So, you know, we need binary populations to make gravitational waves. And a lot of the work that people did kind of in the 2007 to maybe a couple of years ago era was build a binary population just from either simulations using things like Millennium when it was around, and Illustris more recently, or just based on observations in the universe of galaxy mergers, right? We know that there are binary black holes because we see galaxies merging. If galaxies have black holes, then surely those black holes become binaries. So what I'm showing you here is that background strain is almost literally just a sum up of all of the discrete binary signals. And this is some number as a function of redshift, mass, mass ratio, and gravitational wave or orbital frequency. The gravitational wave frequency is twice the orbital frequency, at least for a circular system. But then this also then relates directly to the host galaxy distribution. So if we want to predict binary black holes population in the universe, we can look at the number of galaxy mergers and make some assumptions or based on observations of the local universe for the galaxy mass function and merger rate. And we can use this to project to our binary black hole population. Here's the picture version that I often show instead of the equation slide, which is that, look, we have quantifications both through simulation and observation of the redshift dependent mass function merger rates and timescales, mass ratios of galaxy mergers. You can, using those galaxy populations, put on top something like this, saying we know something about the galaxies, so we know something about the black holes because there's these seeming kind of co-evolutionary links between black hole mass and host galaxy properties. And you know, in an overly simplified way, we can then use this to simulate a supermassive binary black hole population. Now, what I'm showing here is an example simulation from some of the work I did with Joe Simon a couple of years ago. And I'm showing this to introduce the idea of a strain spectrum. So on the y-axis, we have the gravitational wave strain. It's a little bit like the gravitational wave amplitude, but scales linearly with distance. So it's not exactly it's not a flux or anything. And it's as a function of gravitational wave frequency. I've limited this to the pulsar timing band. So this is the decades kind of orbits. These are the weeks kind of orbits. And I've just wanted to point out that each binary in the universe has a dot on this graph. So each binary is orbiting at a particular frequency. It has some separation and mass that defines how strong the gravitational waves are coming out of it. And over time, systems just through emission or through some kind of evolutionary process will evolve from over here, kind of upwards over here as they get closer and closer together, emitting gravitational waves and in spiraling. But the gravitational wave background is, again, kind of sum up of all of these individual strains. Now, I like to show this plot because there have been many, many, many different simulations that have predicted the binary black hole population over the past 1995. What is that? 3 decades? That's wild. But back here, Rajagopal and Romani, that's like the first paper I read when I started my thesis. I was like, this is going to be a great career. And it was really exciting, but that was kind of the only thing for a while. And then as we started formulating ideas about the binary population based on different approaches, we found that there was a pretty big range of predictions for what the gravitational wave background amplitude should look like. Not only that, but also the shape, which I'll talk about a little bit later. But over the same time scale, you can see I have as arrows here. This is a plot made by my colleague Alberto Cezana. You can look at the pulsar timing or search sensitivity, which has kind of fiducially improved over time. And now you can see about maybe year 15-ish, 2015, it looks like the pulsar timing sensitivity suddenly flatlined. Now, this is in the face of new telescopes, new backends that are really fantastically sensitive, an explosion of pulsar discoveries that have grown our pulsar timing arrays to more pulsars. So there's no reason that we should be suddenly flatlining in our sensitivity. By all counts, we should be improving our sensitivity. So it appears that for a couple of years, we've been detecting something that's making us suddenly stop gaining sensitivity. So what is this? Now, this is kind of wrongly a red point there. And again, I didn't make this plot, or else I wouldn't have made that like what looks like a detection, because we don't think we've had like a detection of something. But I'll explain what we're plotting there in a second. Oh, but I did want to point out that, it is really at the point where we're hitting the predictions from a lot of binary black hole population studies that we start to flatline in this space. Now, I wanted to introduce the nanograph collaboration, because that's the one I've been working most recently with the most. And here's a picture from actually earlier this week. There was a big nanograph meeting in Corvallis, Oregon, that I think a number of people were at. I was not. Sadly, I'm not in that picture, but here I am. And the nanograph data set started in something like 2004, 2005, when a couple of pulsar timers got together and say, hey, if we work together, we could really do this a lot better. And after about 5 years, they had this what looked like a really wonderful data set and made a gravitational wave background limit. And over time, this collaboration has grown and grown and grown. And now it's about 120 senior scientists at about 50 institutions around the US. And we have this wonderfully fantastic data set that's just been this career-making thing for many, many scientists over the years. But we've been essentially monitoring a set of pulsars every 3 weeks for the past 2 decades. And I have a statistic here that basically says how our sensitivity should be scaling with the quality of our pulsars. So, we directly scale with number of pulsars. That seems weird. It should be square root of n, but in reality, we're doing pairs of pulsars that give us our detection, not a single pulsar. So we've got sort of an n times n minus 1. So that gets us that scaling. We should be scaling with something like the square root of the time baseline of our data. So the longer we observe, the more sensitive we'll get. The number of observations and the pulsar noise are not as impactful if you've had a very long data set. And there's a reason for this that you can ask me about later. We'll talk about it. Because it seems like, the better time pulsars you have, you should detect better signals. That's true. Anyway, so the nanograph 12.5-year data set is the one I want to highlight right now, because it is the most recent published one. And again, it got published in 2020. I'm going to show you some results from that. But I do want to point out that there's this 15-year data set that adds about a quarter of the length to our data, but most importantly, adds a lot of time for these, these sets of pulsars that originally didn't have a very long time baseline. So the number of pulsars with a long time baseline has really, really increased for that 15-year data set. It doesn't look like a big time addition, but it is actually quite a big impact on our signal sensitivity. So I was showing the strain spectrum before and showing you how, well, look, you have these large separation binaries down at this end of the spectrum. And the evolution of a binary at a very wide orbit is very slow. Okay. And as you get closer and closer, it spirals faster and faster and faster and faster. So you end up spending a lot of time at this end of the spectrum and relatively little time at that end. And that's a well predictable, just by analytic work, kind of spectrum that, at least in the strain space, should be something like strain to the -2/3 in log space. So the slope of that gravitational wave background rises at low frequencies. So if you expect to see a strain background like that, and again, you're kind of thinking of the pulsar residuals as an addition of all of these strains from all of these objects, you should see something that looks essentially like red noise. I don't know how good you are at taking Fourier transforms in your head, but if you're good at that, look at this sinusoid looking thing. That's very long time scale. Look at, if you had a short frequency sinusoid, you couldn't really fit very much amplitude in a short frequency thing. So you can see already just in this data that there seems to be a lot of power at low frequency and relatively little at high frequency. And I wanted to set this up that way just to kind of set up this next plot, which is showing what we call the cross power delay. This is essentially the shared noise signal in all of the pulsar timing data sets. So imagine those 3 pulsars I showed before. We take the Fourier transform of that data, plot a power spectrum, square it, and judge how much power there is as a function of frequency. And pulsars are intrinsically sort of noisy with a low frequency rise. But despite that, with our something like 47 pulsars that we have in the 12.5-year data set, we are able to show that all of the pulsars seem to show a common noise process. And what I mean by that is that it's not only the same amplitude, but also the same spectrum. And what I'm showing here is this violin plot. You can see these gray kind of streaks, which are showing just the likelihood range of noise at each of those frequency bins. Or I'm saying noise, but it's signal, right? It's some kind of sinusoidal signal at each of those frequencies. So this process that we're calling the common red noise process has been identified in nanograv. It seems to rise at low frequencies. Again, here I'm showing a similar range in frequency, something like a couple of nanohertz up to maybe 10 to the minus 7 hertz. And I have, just so you don't read while I'm talking, I'm going to read this. Gravitational waves should be quadrupolar. That's that stretchy, squeezy kind of motion, right? But what we want to do first is search for an uncorrelated signal, which should be appearing in all of the pulsars. If Earth is being affected by a gravitational wave, that's a signal that we'll see in all of the pulsars. And it's the same, if we're affected by many gravitational waves. But this alone isn't convincing of a gravitational wave signal. What we really want to see is that spatial correlation signal from this quadrupolar nature. So this is very interesting, and it is exciting because this could be the first hint of a gravitational wave background. And a lot of us have been thinking about it like that, but at the same time, we're very, very cautious because we've seen things before like this, and we've put them through much more rigorous tests, and they've gone away. So we're kind of undergoing that process now with our 15-year data set, where we have more data now. We're a little bit more sensitive to whatever this process is, and we're undergoing lots and lots of tests. But throwing all that to the wind, if you did want to interpret this as a gravitational wave background, you could, right? You could fit a sort of an amplitude, you can fit a spectral shape, and then you can overplot it on the expected amplitudes and spectral shapes that you would expect for various cosmological sources of gravitational waves. And it seems to be consistent with a binary supermassive black hole population, also could be consistent with cosmic string background and inflation. Again, it's not very constraining, so we can't really discern between those if this is a gravitational wave background. Now, what is kind of exciting is that it seems like all of the other pulsar timing arrays in the International Timing Array Collaboration do see a similar effect. So this was an International Pulsar Timing Array paper that was written that combined old data sets from all of the pulsar timing arrays and ran a similar analysis. And you can see there, they're independently analyzing the nanograv data, old PPTA, old EPTA data, and this is collectively called the IPTA data release 2. Now I say old data because it's not the most current up-to-date data that was available at the time that this data set was assembled. The IPTA is an international collaboration and does suffer some issues of, well, we want to get our own thing first, and then you can have our data. At this point, we have been working in a much more collaborative fashion, and just this has been a long-term development of working out the politics of the thing. So I said we do want to see a quadrupolar signal. Well, what would that look like? Now I'm plotting here what is called the Hellings and Downs curve. Does anybody not know what the Hellings and Downs curve is? I don't want to like over-explain things. A couple of people. Okay, so what I'm plotting here is essentially a correlation coefficient, and it's a function of the angular separation between two pulsars on the sky. So two pulsars, one that way and one that way, are 180 degrees apart, and they should be correlated in the same way with a gravitational wave going through. If they're that way as well, still 180 degrees apart, they should be correlated in the same way with a gravitational wave going through them. And similarly, if you tried to judge one 90 degrees, no matter where those two pulsars are apart in the sky, with a background of gravitational waves, you would expect a particular correlation between those two data sets. So Hellings and Downs back in 1983, I guess it was, actually sat down and predicted this curve and demonstrated what it should look like for a gravitational wave, or sorry, general relativistic standard gravitational wave background. And this is what it should look like. It has this sort of shape where you're more correlated for two pulsars that are coincidental in the sky, and for 180 degrees apart, but anti-correlated at this sort of 90-degree mark, with these two zero crossings somewhere in the middle. And I'm showing here our 11-year data set, Hellings and Downs plot. And nobody would look at that and say, wow, that looks really convincing. The 12.5-year I kind of feel the same about, as does all of nanograv, but it does look a little closer. And it looks close enough that we say, judging by the Bayesian evidence for this, that it's at about a 2.5 sigma level of evidence for something that fits that shape. And 2.5 sigma is not strong. We've been working very hard with the international collaboration to lay out a set of detection thresholds and protocols. This involves data analysis techniques, including, like move your pulsars around in the sky. Does that make the detection go away, or is it still there? If it's still there, that's not a good sign. Changing the distances of pulsars and seeing if that changes the signal. We have a rigorous set of tests, but we also have a requirement of something like 5 sigma. And I'm just going to tease that I think on April 7th, that detection protocol list is going to be posted to arXiv. So watch out for that if you're interested in this field of how we think a rigorous test should be done. I also wanted to point out that one of the pulsars are always cool, but one of the cool things about pulsar timing arrays is that you can actually detect clock errors on Earth. So all of the telescopes on Earth are linked to a maser, which is then linked to UTC time, which is corrected by atomic time. Now, if all of the atomic clocks on Earth were wrong for some reason, we would actually be able to see that as a monatomic drift in all of the pulsars. So all of the pulsars would have the wrong time of arrival, and you would see a jump in every single pulsar. This does not seem to be what's happening in this data set. This signal is not monopolar, which is what happens with a clock error. It also is not dipolar, which would happen with solar system errors. Can you think of why this would be dipolar for solar system? This is like, we don't know where Earth is in its orbit around the sun. Any idea? I know you guys probably won't speak up. What's that? Yeah, Jupiter or something. Yeah, like planets, right? Everything's along the ecliptic. So if you're shifting side to side in the ecliptic plane, you would preferentially be moving in that plane, and you would have correlated signals along the ecliptic plane, but not orthogonally to the ecliptic plane, where you're not having any, proper radial motion compared to those pulsars. So we are able to fairly confidently rule out solar system errors in our modeling and clock errors. Now I'm showing this plot from Javi Siemens back in 2013, showing how bright we would expect to detect a gravitational wave background or any type of shared common signal at a particular slope. And that is where this detection statistic comes from, and that scaling. And this is basically showing that from time 0 to something like just over 10 years, if we get to the point where we have our data, we're raising our number of pulsars, we're improving our pulsar measurements, so we're lowering our little sigma pulsar noise. We should get to this point where our sensitivity is asymptoting towards this underlying signal, and our sensitivity should roughly scale with time according to this line. That seems to be what's happening from our 11 to 12.5-year data. And now, of course, going forward, we're all really holding our breaths to see what happens with the next data sets, because we think that this will really make or break this field and may change things. But so I already said that soon the detection protocols document should be released on arXiv. We have a coordinated plan internationally to release a next wave of pulsar timing array data and analyses, and this includes the nanograv 15-year analysis, separately for all the pulsar timing arrays, but in a coordinated way in about a month, maybe 2, maybe 3. These things sometimes encounter delays. But this is to say, invite somebody back maybe in a couple months, or at least find somebody to give a talk in a couple months, and they can update you on all of this field and say, look, actually, we found this was some kind of weird pulsar effect, or we've detected a gravitational wave background. One or the other, something's going to happen. And later on in 2023, we are going to have this really wonderful data set where, like I said, we're now working much better together, and we have somebody, Deborah Good. I don't know if Deborah has come here. I think she has, right? Yeah. So she's working with Chiara on this very up-to-date data release 3. And it's just going to be so fantastic. Oh, hey, Deborah. Good job. All right, so part 2, binary black holes. So now we get in, this was all pulsar timing arrays and data analysis and things. Now we get into the messy fun astrophysics and detecting supermassive black holes and kind of understanding how they link to things like galaxy formation. So, I already said we get a population of binaries from the fact that we have galaxy mergers in the universe, right? Also, I'm always jealous of this simulation shown on all the screens here. So there's my simulation that I didn't make, but it's beautiful. So track the binary in this interaction. There's a crossing. A lot of the gas gets stripped off of that binary. A lot of the gas gets upset. Stars get flung into the center. There's a lot of funneling of material onto this central location where these 2 black holes end up. And over time, you have processes like dynamical friction that's driving the galaxy merger, but also driving the 2 black holes down to the center. At some point, they form a binary, undergo further processes, and start emitting gravitational waves, which drive them to coalescence. Now, I hate the title of this slide because this is not really a problem anymore, but what I want to do is reappropriate this term. And I'll introduce the term first for those of you who haven't heard it. So I'm plotting here what amounts to the binary in-spiral timescale as a function of binary separation. And you can see out here, it's something like a radius being just the separation between 2 black holes of 100 parsecs. You get dynamical friction that's still kind of acting with the, the broader gas and stars from the galaxy. Early modeling, and this was from a paper in 1980 that kind of set this field in motion. Early modeling was saying, well, there's really only a couple of processes that can really drive these 2 black holes together. And the main thing is stellar interactions. So if you have a star that comes in, it interacts with that binary black hole, the star will typically get thrown out, carry away energy, but then also carry away the star, and it's not going to come back for a very long time because it's been flung out at high velocity. And it was recognized that from the kind of interaction cones, loss cone, where you're feeding this binary black hole and those 3-body interactions, you would actually run out of stars. And it could be that your loss cone is depleted and you essentially keep a binary just sitting there in orbit at more than Hubble time. So this stalled binary black hole system. At this point, nobody really thinks that happens anymore. I think there is some sense that it might for some systems. But generally, it's been realized that if you take some kind of realistic galaxy shape, like a triaxial galaxy with triaxial orbits, you don't actually get loss cone depletion. You keep feeding stars into the center. So 3-body interactions can continue at some meaningful rate. You also have gas that's coming in and driving the evolution of the binary relatively rapidly to coalescence, or at least to the regime where you're emitting gravitational waves. And if those things fail, at some point, you're just going to get another galaxy coming in and drive that binary to coalescence. Now, what I'm trying to reappropriate the term last parsec problem for, because I think it's a good phrase, is that we don't really know what drives the binary's evolution here. And something does, probably. We don't see strong evidence of 2 black holes in the centers of all galaxies. But the reason it really matters for pulsar timers is that it will actually influence the sort of change in orbital separation over time, especially at these early separations. So remember that strain plot where I was saying they actually spend a lot of time at large separations and relatively little time at small separations. If they're being driven by gas really quickly through this early phase, you won't actually have as big of a population there, and that will affect your gravitational wave background spectrum. So, how do they get past this point, that last parsec? How fast do they get, and how much material are they really still interacting with? This can also really drive a change in the way we expect to see continuous wave signals. So traditionally, we've modeled continuous waves as just circular systems. By all LIGO accounts, you should have a circular binary by the time you get to be emitting gravitational waves, because gravitational wave emission is just circularizing in just a few orbits. But if you have continued gas interaction, this can drive relatively large eccentricities that you then have to model for and use a lot of computational power to try to detect. So here's my very cartoony way of showing how all of these environmental effects might change your background. So here I'm showing this just fiducial, driven only by gravitational waves kind of background. So that's just an example of galaxy evolution model. Let's say you have a limit from your pulsar timing arrays that's something like there. Well, maybe you could just totally lower this entire spectrum, right? So we're changing the amplitude of our spectrum by saying, oh, almost all the black holes stall, so none of them actually get to the gravitational wave regime. We don't think that's happening. Maybe we don't have this big of a mass of black holes as we expected. It's also possible. It's also possible we could turn the assumption that almost all galaxies have a black hole in the center on its head and say, actually, only half of galaxies have a black hole. So there's a couple of ways you could just cinch down the complete amplitude of this background. And you can see how these pulsar timing limits can influence something like that. But pulsar timing arrays are a little bit better than that, because not only will we detect the amplitude, we will also detect spectral shape and curvature if we detect a background over the next something like 5 to 10 years as we get more data and are able to get multiple distinct spectral data points across this. And at that point, if we do see turnovers here, this is this effect where we're driving at binaries very efficiently through this early phase and not seeing as much signal at this low frequency. So we get effectively a turnover in the spectrum. And this is almost always due to some kind of environmental coupling at that early phase. So extended stellar interactions, gas-driven in spiral, eccentricity in the binaries that redistributes the power. And the shape of the spectrum will give you that information. So I wanted to spend a little bit of time talking about continuous gravitational waves, because this has been all about backgrounds. And we do expect to detect something like 2 to 10, what I'm calling discrete sources. I hate to call them individual since they're binaries, but discrete sources by 2030. And I'll show you some modeling for that. And from something like 2034, LISA should begin really detecting hundreds of targets, if not more. So this was a study led by Chiara Mingarelli of your own fold, but that I worked with her on a couple of years ago. And what she had done was take the 2-mass survey of galaxies and run a prescription to say, okay, well, look, we know something about this galaxy. Let's assign a probability that it should contain a binary supermassive black hole. She then was able to compare this with the predicted sensitivities of pulsar timing array data sets going from what was then 2019 up to something like 2029. And then say, okay, well, look, let's make 1,000 universes and see in what fraction of universes we actually expect to detect a couple of systems. And one of the nice things she did was actually assign a detection confidence as a function of year for systems. And the outcome of this is that you can see in 2019, which is a couple of years ago, we really didn't expect to see a signal. Based on just the density of galaxies in 2-mass, by 2024, which is next year, we actually have a reasonably good chance of getting something like a 2 sigma detection of a binary, if this prescription is correct. By 2029, these numbers all go up to 100% because that sensitivity of pulsar timing arrays is just good enough if it scales as we expect. So what would a continuous wave look like? Well, I'm kind of, saying, well, it would be a sinusoid, but in reality, this is going to be sitting on top of some kind of other background noise, and neither are going to be this extreme, but you get the picture. And if we thought about this in terms of the spectrum, each of these points, if this is binary black holes, would be made up of some large number of binary black holes. But if there were a really whoppingly bright one, like the one I simulated there, it would set one of these points like way up here, right? It's going to show that everything has a sinusoid at that intensity. So, it might look something like that, but just much more extreme. And, we think that's a noise feature, not to get too excited about that. But that is a version of what you might see. So I wanted to, I feel like I missed a slide. I wanted to just walk through some of the work I've done in continuous wave detection, because what we've been trying to do is think about how we can actually be more sensitive to continuous waves and just explore that idea. So I'm showing here the multivariate parameter space that we try to search to detect a continuous gravitational waves. And here we actually have a binary signal model. So we have our sky position, gravitational wave frequency, just some geometric terms, what's your phase at a certain time, what's the inclination, what's the gravitational wave polarization, that's that little thing. This is the chirp mass combining both the masses of the black holes and of course the distance, which all go into defining how bright the strain for this source will be. So that last term is kind of redundant, even though that's the thing we quote. We also really don't have a good handle on pulsar distances. So if we want to calculate the pulsar term, that's actually some part of our search space that we have to search over. And this is currently a minor effect in terms of how it influences our searches.
One parameter, is there a larger dependence on one parameter versus another?
Yeah, there are. So, and I'll talk about that in a little bit, but essentially the gravitational wave frequency is kind of the most influential thing. Right, so I'm showing here a plot of basically if you just had one gravitational wave source on the sky, what is going to be the response of the pulsars in our pulsar timing array. So this is just RA in this direction and DEC as the latitude there. Those white stars and the orange and red star, those were the poorly behaved pulsars, so they got colors. But the white ones are the rest of the pulsars in our 12.5-year nanograv data set. And we've stuck a big whopping gravitational wave source there on one point in the sky. And you can see that in these continuous wave searches, we don't just have spectrum, we also have sky resolution, right? So that gives us a little leg up. And one of the studies we've been doing a couple of years ago, back in 2020, we published this with my student, Caitlin Witt, who's no longer a student. She's a wonderful postdoc over in Chicago. But one of the things we did was try to say, well, look, there are a couple of sources that we think might actually be binary supermassive black holes. And people have gone out and measured their orbital separations, they've measured their periods, they've inferred masses. We know where they are in the sky. We know how far away they are because it's very easy to get a redshift. So what if we actually use those to set constraints on our search space? And this is an example of one of these sources, 3C66b, and it's very famous because it has this period that's something like 1.05 years plus or minus 0.03 years, which is awfully suspicious because it's very close to 1 year and involves motion on the sky. So, whether this source is believable or not, it was expected originally to have a chirp mass of something like 10 to the 10. And that involves basically, 2 10 to the 10 solar mass black holes, which is huge. But what we can do is use the measurements that were made of this source and the inferences made by measurement of the electromagnetic emission to set constraints on the priors going into our Bayesian search pipeline. So, sky position is a total given because we know where it is on the sky. Distance is easily found through redshift. For this source, we did have a fit to the gravitational wave frequency. And for some targets, this is true from other sources as well. But essentially, we are able to halve the parameter space. And I'm just showing here how this sort of played out. There was a model that had this source originally very, very bright. We, of course, ruled that out completely. That had been ruled out before by just a single pulsar limit. But we didn't quite get to the lower mass model that was made for this source. But we did actually demonstrate that this type of search where you're limiting the parameter space could be improved by something like a factor of 2 over a blind search of the whole sky for continuous waves. And I'm showing here really the most important parameter, like I was saying, is the frequency. And this is weird axes, so let me describe them. So this is the mass of the system, the chirp mass. And on the x-axis here, we have the prior width. So this is essentially, we've measured it perfectly. This one, we've measured it within a factor of 1 in log space. So within a factor of 10 or something. And you can see that if you had a completely unconstrained mass limit, you don't do very well with your sensitivity limit. But once you have a pretty good constraint, even a really kind of poor constraint on that frequency, you know roughly what it is from electromagnetic emission, you can get a really big improvement of this limit on mass. And this equates to something like a factor of 2 in strain sensitivity. Now, we also have been doing just what we call blind searches, where we say, okay, well, let's not assume anything about the binary population or anything about its frequency. What we're going to do is search for a binary anywhere on the sky. And what I'm showing here is Again, kind of a similar plot to what was before, except what I'm showing here now in color is the sensitivity of nanograv. This is the 11-year data set and the 12-year data set, 12.5 year, that should say. And this is the distance out to which we could see a double 10 to the 9 solar mass binary black hole system. Now, when I was a kid, we used to play this game of like, what's wrong with this picture? What do you guys think's wrong with this picture? It's a little subtle. I'll give you 5 seconds. What's that? I'll give you a clue. This one has more pulsars. We should be a little bit more sensitive. Do you give up? What's that? Yeah, so the scale only goes out to something like 85 here. So between the 11-year data set and the 12-year data set, where we've gained like double the number of pulsars, we've gained a couple more years of data, at least a year and a half more of data, we've actually gotten less sensitive. What is happening here? So when we first noticed this happening, we of course went back and said, oh, we're so bad at coding, like we have to fix our code and figure out why this went wrong. It turns out it wasn't the code at all. What it was is the fact that at the frequencies, so these maps are made at one particular frequency. This one was made at 8 nanohertz. This one was made at 7.65, or about 8 nanohertz. At those frequencies, you actually have an underlying common red noise process that's existing. And what we then did was just take a difference of the map sensitivities, and this is just a difference between those two maps I showed you before. And it shows that for some points in the sky, we are actually improving our sensitivity. So blue here is a better sensitivity, like our strain has actually gotten better, our strain limit. For the rest of the sky, our strain limit has gotten worse at those frequencies. And I'm showing here the detection of common noise that you see. So for that, if you're not modeling this common red noise process in our continuous wave search, we get these purple points. And we actually say, look, we've actually detected a bunch of sinusoids at low frequency. But of course we haven't. We've just detected this common red noise process down at those low frequencies. And what that translates to is a frequency-dependent horizon limit that we see bending down at those low frequencies. So you see, even for the 5, 9, 11, and 12.5 year, this is partly just due to the non-sensitivity of our data set at those frequencies, but it also has to do with that common red noise process. And I'm showing the 8 nanohertz line there. But you can see overall, our sensitivity has improved at high frequencies as we would expect it to, given the noise in our data and given the relatively small increase in time baseline we've had. Now, I don't want it to sound like I've actually said we have a horizon limit, because that is not like, 85 megaparsecs is not our horizon limit for detection. That was specifically made for 2 10 to the 9 solar mass black holes. And what I'm showing here is a simulation run by Luke Kelly a couple of years ago. And what he's plotting here is 5 different realizations of the universe. And he's only plotting the brightest gravitational wave source of a binary in each bin. So if you have, binaries here, he's then created the background, not including that brightest source. So you can see those lines are the background. And any of these points that has a black circle around it is what he's calling a foreground source. So I did want to point out that there are sources here that stand out potentially above the background, because they contribute something like more than 50% of the power to that particular frequency bin. Now, if the signal we're seeing in the nanograv data is not binaries, it is possible that this sort of thing is not happening, and we're not actually able to see continuous waves above whatever other noise process this is that we're seeing. If that is all due to pulsar noise, we're not going to see binaries above it. And I wanted to just lay this over the 2DF survey to show you how grim this situation would be. I hate to like say bad news, but so here's like the worst point in the sky for the 12.5 year data set. This is a redshift equivalent of about 0.01, something like that. And that's, something like 10 to the minus 4 cubic gigaparsecs in volume. And if you just run a standard galactic density, number density, this is like something like 300 to 1,000 massive galaxies. We're only sensitive to like a couple thousand galaxies. The best location in the sky at 12.5 years, that's a little bit better, We get a fraction of a gigaparsec and about 15,000 massive galaxies. But if we actually go and do, electromagnetic enhanced emission, we look at high frequency, so we're not running into this common red noise process, we can push our horizon limit a little bit further and get something like probing 200,000 galaxies, which is a good number. So even then, we do have some chance at doing continuous wave emission. But I did want to point out, I'm going to go back now to Luke Kelly's study, which is that the peak source in each of those bins was not necessarily a 10 to the 9 solar mass black hole. And I'm showing here, just focus here on the red bands here. These loud ones are the ones that are sort of like the foreground, the loudest source in the bin. For a bunch of the frequency range, for much of the frequency range, those sources actually lay between something like 0.4 and 1.3 in redshift. So they can be relatively distant sources. And the reason for that is you have a much more likely chance of getting two very massive galaxies combining at those high redshifts, where first the galaxy merger rate is peaking, and also you just have more of a chance of getting a double very massive black hole because you have more volume you're covering. So we might actually be able to see bright sources much farther. So I realize I'm running out of time. I just wanted to point out one more thing. Oh, that's such a cool animation. Ask me about it. If we did want to find other continuous wave sources through electromagnetic emission, there are a huge number of sources that have been detected and claimed to be a binary in some way. And I'm just showing some random graphics of those. One of the big efforts we're doing now is trying to organize for the oncoming era of binary supermassive black hole science, both through pulsar timing and through the many, many, many surveys that have been done and are about to be done of the sky as a function of time. So me and my student Jessica Sidnor are now working on this thing called Bobcat, which actually had the first seeded idea here at CCA in a conference back in 2018 when we first came up with this idea because everyone was complaining that this doesn't exist. And the idea of this is basically tracking all of the binary sources, looking at all of the different evidence for their emission, and being able to have this database as a resource for anybody who has means, has a reason to use it, but also in a way to link directly with the pulsar timing sensitivity limits, which is not directly done these days. And currently, Bobcat, we're calling this binaries orbiting black holes orbiting black holes catalog, Bobcat. There are currently 800 papers claiming a binary black hole detection, or claiming, oh, that binary black hole is not a binary black hole because of this observation we've done. And this amounts to about 500 distinct sources currently in our Bobcat list. And I did a very kind of loose thing here and just put our old nanograv sensitivity curves. I put an indication of where our common noise process is and put stars for a randomized gravitational wave frequency and 10 to the 9 solar mass black hole binary. In reality, each of these binaries could be anywhere along an ISO contour along that line, because if they're higher frequency, they're going to be a little bit brighter. So those are kind of the span of sources. Oh, there's IPTA data release 3. It's going to be a little bit more sensitive. And you can actually see that we will be able to meaningfully probe a fairly large number of binaries here. And the situation's even better if we assume that these are all 10 to the 10 solar masses. Of course, they're going to be a lot brighter. Going on into the future, it's going to be really a fantastic era for binary supermassive black hole multi-messenger science if pulsar timing arrays are able to detect binary supermassive black holes. With a huge number of wide field surveys, but also time resolved surveys, they're going to be tracking, flux variation and morphological variation of these sources. And that is it. So stay tuned in the coming months for the next wave of pulsar timing array data releases. It's going to be an exciting year for it, no matter which way it goes. The continuous wave horizon, we think we're probably going to need some new modeling approaches to figure out what to do if this common noise is or is not binary supermassive black holes, but also electromagnetic detection can significantly improve detection prospects. Thank you all.
Awesome. Thank you, Sarah, for a really engaging talk. We have 5 minutes for questions. So people on Zoom, feel free to unmute yourselves or type your questions in. Do we have questions in the room? While people gather their thoughts, I mean, it's really tantalizing to see the pattern that almost suggests scalings and downs. So are there ideas for what it might be if it's not Helens?
Yeah, so, we have a laundry list essentially of what it could be. The one that scares me most is the idea that, we don't really understand neutron star interiors. And it's possible that there is some underlying physical process that forces pulsars to all obey the same variations with time. To me, that's a real possibility. It shouldn't be quadrupolar on the sky, of course, but that might give a common noise process, and that 2.5 sigma is not significant enough to yet really rule that out. So it'll really be the next data sets that test that. That's a good question.
Is the limiting factor in determining the quadrupolar pattern the distribution of pulsars in the sky? I imagine if you had a better coverage in the sky, maybe even the better.
So I think, yeah, it sort of is the answer to that. So each of those bins, let me get to those bins pictures. Each of these bins has averaged over however many pairs there are within that bin. So the more you have, the better an average you have, so that that error bar will go down a little bit. But it also depends on the underlying noise processes. Even if you do have a pure Hellings and Downs curve too, though, it's never going to be perfectly along the line because of that uncorrelated pulsar term. So there is an underlying noise that you expect to see on top of that. What's that?
It's way smaller than.
It's way smaller, and actually, I think it would be expected to be the same kind of fundamental size all across the angles.
So,
You want to use your mic?
Yeah, let's do that. Just in case. Good. If there is a continuous wave source, is the Hellings and Downs curve calculated as a function of frequency, and that's why a continuous wave source doesn't mess it up?
So a continuous wave should also have a quadrupolar correlation. So in principle, should still look like this.
Okay.
Yeah. So it shouldn't mess it up. I mean, this is made of, in principle, if the Hellings and Downs curve would be made of many, many binary black holes.
Right. Maybe the question is it calculated as a function of frequency, like gravitational wave frequency?
Oh, I see.
Do you calculate a Hellings and Downs curve at each frequency?
No, because it's created as a correlation between a time series, essentially. So, red noise in each pulsar, but you cross-correlate those.
Thanks.
Yeah.
Any other questions? Oh, we have a question by Yuri online. So Yuri asks,
Hi, Yuri.
How will you tell between binary black holes and cosmic strings?
Oh, good question. So, I mean, fundamentally, to me, I think we would have to detect a continuous wave to tell between them. I don't think there's any reason a string should show a sinusoid. You could arrange for that, I'm sure, but I think it would be more likely to see a binary black hole as a sinusoid, and also, of course, identifying its host galaxy and showing that it actually has electromagnetic emission that's in the center of a galaxy. All of that would be pretty fail-safe evidence that you are in fact seeing a continuous wave, and if you're seeing a continuous wave, you're for sure seeing a background because it can't be that far behind. The other way, and that's a little bit less discriminating, is the spectrum. So looking at the shape of the curvature of the spectrum. If you see curvature, that's probably more likely to be from binary black holes. And then I guess the final answer I would say to that is wait for LISA, because LISA will be able to detect cosmic strings if we are detecting them. I think that's a true statement.